continue with linear regression, I just quickly wanted to present a few slides showing that, in fact, the least squares formalism, which we've just seen, is nothing else than maximum likelihood estimation, or MLE. Now, this might be something rather technical for some of you, so feel free to skip it, but I think it's quite useful to get a better understanding. And we will see later, in particular, we will see tomorrow when looking at classification, that actually when we look at classification, then the idea of least squares doesn't really make so much sense anymore, but the formalism of maximum likelihood is something more universal, which we can still apply for the case of classification. So it is at least useful to have a look and see how this formalism works, and that in this case is just equivalent to least squares for the linear regression problem. So what we basically do is we look again at our kind of line of our true linear relationship, and our observations we have here 1, say 2 and 3, and obviously those 3 observations were off by an error epsilon. Say there was epsilon 1, say this thing here is epsilon 2, this thing here is epsilon 3. So say those are my 3 observations, and now I'm basically assuming that those errors are independent and they're identically distributed, so they're all coming from the same distribution, and that those are normal or Gaussian random variables. So basically this is my assumptions. They are Gaussian random variables, they have mean 0, so are equally likely to be above or below my true line, and they all have the same variance. So it's not like at one part of the line, say further down here, I'm kind of likely to see observation which a much higher variance, and here with a much lower. So I assume they all have the same variance. So I'm making those assumptions now, but we will see that the least squares formalism already had all these assumptions implicitly embedded, but we just didn't see it. So it's clearer in this formalism because we're making very much clear what are actually the assumptions underlying our framework. So if I assume it, I can now write down the likelihood. So likelihood, if you haven't heard it before, might sound kind of, you might ask, oh, what's that likelihood? But it's nothing else than the overall probability of seeing those observations. And if they are independent, then it's just the product of the probabilities. So imagine I have a simple case. I have, say, 50% probability that event 1 happens, 50% probability that event 2 happens. So what's the probability that both of them happen? If they're independent, it's just a half times a half, a quarter, so it's 25%. In the same way here, so I have the probability that this first value was very far out, which is in a sense p of epsilon 1. Then I have the probability that this second value was down here at the bottom, which is p of epsilon 2, the probability having observed this specific value of epsilon 2, and so on and so forth. That takes the product of all of them, and each of them is a Gaussian. So Gaussian, very importantly, is just some constant, and then I have e to the minus epsilon I squared over 2 times the variance. Again, the constant doesn't really matter for our case. It's just a normalization that the probability kind of sums to 1. But in any case, so now epsilon I can actually replace this with y minus f of xi, because I know that this point at the bottom here is just f of x1, and this at the top here is y1. So the difference epsilon I is, or epsilon 1 in this case, is nothing else than y1 minus f of x1. So I have this relationship, and I can just plug it in here. And now I want to show you that this is nothing else than actually the least squares formalism. So we have the likelihood, and what we want to have a look at is that this relationship now gives rise to the least squares formalism. So so I have likelihood, let's just call it, to make it a bit easier, let's just call the likelihood equal to L. So I have L, and what do I want to do with the likelihood? For the least squares, it was kind of intuitive that we wanted to minimize the least squares. We want to have the line closer. Now for likelihood, we want to find the model, the underlying true line, which makes the observed data most likely. So what's the model which makes it most likely to have seen what we have shown, basically? So this is what we're looking at. So we really want to find the maximum here. So we want to find the maximum over the parameters. Remember that f contains the parameters. F of x is just a relationship. So f of x would just be something like x matrix times a. So this involves the parameters a. So I want to maximize over all my parameters a the likelihood. So I want to find which a maximize the likelihood. So maximizing the likelihood is nothing else than maximizing this product there. But we can actually see, if we plug in what we have here, we see that if you just look at what L is, so L is just this product, but we can plug it in. So there's some form of constant here, and then we effectively have the product over I, and then we have the exponential of yi minus f of xi squared over 2 sigma squared. So this is what I want to maximize, but I also know that the product of an exponential is just the exponential of the sum. This is a very simple relationship. So I have that this is equal to some constant here, and then I have times the exponential, and then I have 1 over 2 sigma squared, and I have the sum over I over yi minus f of xi. Now you can already see the term from the least squares emerging, and now what I basically know is that to maximize L, so maximizing L is effectively the same as maximizing the log of the likelihood. I mean, the maximum value will obviously be different, but if I'm asking about the argmax, what is the value of A that maximizes L? It's the same value of A that maximizes the logarithm. So this is actually kind of equivalent to maximizing the logarithm of L, which is something much easier to work with. So if I take the logarithm of this expression above, I can actually say that the log likelihood, which is sometimes called little l, which would be the logarithm of L, this is nothing else than it's a logarithm of some constant, which is yet another constant, which I don't care really about, plus, and then I have 1 over oh sorry, I'm forgetting a minus sign here. Here's a minus sign, here's a minus sign, and then obviously here's a minus sign, 1 over 2 sigma squared, sum over I yi minus f of x of I squared. And now I can really see the relationship. So maximizing the likelihood is the same as maximizing the log likelihood, and actually this is a constant, so it doesn't really matter. So to maximize the left hand side, all I have to make sure that I maximize this term here, but this is with a minus sign. So for this whole term to be maximum, effectively the term with a minus sign must be minimal there, and this constant again doesn't matter. So I want to find the minimum of this. So what I've really seen is that maximizing the likelihood is effectively equivalent to minimizing this term here, which is nothing else than our familiar expression from least squares. So, oh, I apologize, there's some delay in this showing up what I've right now written, so hopefully it will show up in a second, or not. Oh, here it is. So what I've just written, so maximizing L is equivalent to minimizing this term here, which is least squares. So effectively, maximum likelihood estimation, as we have just seen, is equivalent to least squares. And this is just something useful to know. You might have seen this derivation before, but it's just that so least squares, which has a very intuitive interpretation, is often presented first when you learn about linear regression because it makes sense once you look at it. But actually, it's not very transferable. You can't very easily transfer it to other cases such as classification. Maximum likelihood might be maybe more complicated at first, might look less intuitive at first, but it's a more general framework which we can apply to other cases as well. And it also makes the assumption clearer. So here we knew, for example, that our assumption was that that firstly I have IID observations, so all my observations are Gaussian. Only because they are Gaussian do I have this square here. If there would be a different distribution, I would have a different loss function here. For example, if I wanted the one which has the absolute value rather than the squares, I would have to use a distribution which is not Gaussian but with an absolute value, something like Laplace distribution there. Also, I can only take out this term here because sigma, the variance, does not depend on I. If each observation had a different variance, I couldn't take it out and I wouldn't have standard least squares. I had some form of weighted least squares then. But this is just to show that maximum likelihood might be a nice way of looking at linear regression. It's a bit more formal, but it tells you a little bit more about what's going on. And with that, we can now move on to the bias variance trade-off.